This question compares possible designs for a new computer network between multiple school buildings and whether they meet specific requirements. A school's administration team decides to install new fiber optic internet cables underground. The school has 8 buildings that need to be connected by these cables. A map of the school is shown below with the internet access point of each building labeled from A to H. Jonas is planning where to install the underground cables. He begins by determining the distances in meters between the underground access points in each of the buildings. He finds that distance AD is equal to this value, DF is equal to this, and the angle ADF is equal to this. And question A, find AF, 3 marks. So you can see that 2 sides are given, 1 side is required, and also an angle is given. How to connect 3 sides and an angle using cosine rule. Formula is given in the data booklet, and since there is only one given or known angle, it's D, and we should write a cosine rule for the opposite sign. It's not because AF is required, it's because D should be involved, and that's why we write a cosine rule for side AF, because in general there are 3 possibilities, 3 sides for which we can write a cosine rule. And cosine rule says that any side squared, and since we write cosine rule for AF squared is equal to the sum of squares of 2 other sides minus 2 times these sides times cosine of the angle between them, and you can see that this side and this angle are opposite. And substituting values and using a calculator, the right hand side is equal to this, then a square root or to the power of a half or 0.5, and you can see that it's 129 meters to 3 significant figures. And the next, the cost for installing the cable directly between A and F is this value. And question B, find the cost per meter of installing this cable, 2 marks. So cost per meter is just total cost divided by distance, and it's just this given value divided by found distance AF, and it's just given total cost divided by the answer, and you can see that it's 165 units are not required here. And Jonas estimates that it will cost $110 per meter to install the cables between all other buildings. And question C, state why the cost for installing the cable between A and F would be higher than between the other buildings. 1 mark, and you can see it's because there is a lake in between, and any reasonable answer, for example, is because cables would need to be installed under the lake or under the water. And the next, Jonas creates the following graph as using the cost of installing the cables between 2 buildings as the weight of each edge, and DI. By using Kruskal's algorithm, find the minimum spanning tree for S, showing clearly the order in which edges are added, 3 marks. So we start with the edge with the least weight, and you can see that it's EC, and it's and again we need, or we should consider, the edge with the least weight among the remaining, and it's what it's G. And actually, what is the difference between the Kruskal's algorithm and the Prim's algorithm? And difference is that if it would be the Prim's algorithm, the starting vertex it should be given, but the next vertex to be added, I should consider edges which are connected to existing network. So I can consider these edges, and I should choose with the least weight. But for Kruskals, I can consider edges everywhere, and I need the edge with the least weight, and it's DG. We need DG because D and G are not in our network, so DG. The next is DB. The next it's AB. The next is DE. BDE. We need DE because we need network, they must be connected. And the next it's EH. The next is what this one, but you can see that G is already connected and H is also connected, so we don't need GH, and also we don't need GE, and actually there is only one remaining unconnected vertex, it's F, and the least weight is for FD. And the next question, hence find the minimum installation cost for the cables that would allow all the buildings to be part of the computer network to max. We need just what? Add all these values up, and it will be the total cost, because each vertex, each edge represents the cost, and we need just the total cost of this the minimum spanning tree, and it's this value. The next, Jonas wants to create a Hamiltonian cycle within the graph, and question E state why a path that forms a Hamiltonian cycle does not always form an Eulerian circuit. 1 mark. Hamiltonian cycle, it's about what? To visit all vertices, and an Eulerian circuit, it's about what? To visit all edges. And we can say that as it means Hamiltonian cycle does not have to include all edges of the graph, only all vertices. And the next, F, starting at D, use the nearest neighbor algorithm to find the upper bound for the installation cost of a computer network in the form of a Hamiltonian cycle. Note, although the graph is not complete in this instance, it is not necessary to form a table of least distances, 5 marks. So we should apply the nearest neighbor algorithm to find the upper bound for Hamiltonian cycle and how it works. we start at D, and we should find the nearest neighbor. It may be A, B, F, G, or E with and definitely the edge must be with what the least weight, and it's what is D? No, it's not D, it's DG. It's DG. So it's DG. The next, from G, we find a neighbor with so that the edge is with the least weight. It's to H, GH. The next, from H, it's to E. Then to C, and you remember that all vertices must be visited once, and C, then definitely only one variant to B, then to A, and then to F, and then to D. D. It's the start and the end point, and FD is and hence the upper bound. You need just what? To add all these values up to get the result, and it's F, the upper bound. And G, by deleting D, use the deleted vertex algorithm to find the lower bound for the installation cost of this cycle 6 marks. By deleting D, so we delete vertex D and all adjacent edges. So we delete D and these, and this. And for remaining graph, we do what? The minimum spanning tree, it's not specified, it may be by Kruskal's algorithm, or also maybe by Priam's algorithm, but I will do by Kruskal's algorithm again, and we need the edge with the least weight, and you can see that it's EC. Then AB, then CH, then GH, then you can see that E, G not required because G is already in the network and E is also already in the network. And the next is BE, and you can see that there is only one unconnected vertex, it's F, and it can be connected by this AF, but it's larger, so it's F, G. And to get the lower bound, we should add two edges from D with the least weights, and from D it's plus D, G, and plus B, D. And add all values up plus these two edges, and we get the lower bound. The next. After more research, Jonas decided to install the cables as shown in the diagram below. Each individual cable is installed such that each end of the cable is connected to a building's access point. The connection between each end of a cable and an access point has a 1.4% probability of failing after a power surge. It means rapid increase in voltage and power, so it can be damaged, and probability of fail is 1.4% or this value. For the network to be successful, each building in the network must be able to communicate with every other building in the network. In other words, there must be a path that connects any two buildings in the network. Jonas would like the network to have less than 2% probability of failing to operate after a power surge. So it's a probability of fail for each individual connection, and we need overall probability that this network fails. Probability should be less than 2%. And question H shows that Jonas' network satisfies the requirement of there being less than a 2% probability of the network failing after power surge. 5 marks. So probability of fail, it can be found as, actually there are a few ways, but I want to find as 1 minus probability of no fails. And no fails, it can be what? Probability that zero connections failing, it's one connection failing, or minus probability of one connection fails. What does it mean? It means that if, for example, these fails, you can see that all are still connected in the network, and also they all still be connected if there are two fails but within one wire between two consecutive vertices. So it may be like this. So it may be minus probability two connections fail on the same wire. And hence it becomes 1 minus probability that no fails, and you can see 1, 2, 3, 4, 5, 6, 7, 8 vertices and 2 connections, so 16 in totals. 16 in total, and no fail if probability of 1 to fail, so no fail, it's 1 minus this value, and it's this, and to the power of 16. There are no permutations between these 16 events, so all 16 events, it's no fail. Minus 1 connection fails. 1 out of what? Out of 16, and 1 fails with no probability, and it means that other 15 must what? No fail, so no fail other 16, but there are permutations because this fail may be at any of what, 16 positions, or it's a combination, number of combinations 1 out of 16, or just 16. And minus 2 connections fail on the same wire, and you can see that there are 8 wires and 2 fail, and the remaining 14 don't fail. And if you calculate it, you get this value, which is less than 2% as required. And that's all for this question.